Welcome to the Ultimate Physics channel. The topic of today's video is relativistic energy. Let's do a quick recap of the concept of relativistic energy before moving on to solving some problems on the topic. In special relativity, total energy and momentum E and P are conserved quantities in an isolated system, and the rest energy is invariant. The velocity and kinetic energy are both neither conserved nor invariant. That makes the quantities E and P both more fundamental than even velocity and kinetic energy. The relativistic expression for total energy is given by E is equal to mc squared over square root of 1 minus u squared over c squared, where u is the velocity of the object itself and c is the speed of light. M is its so-called rest mass. This results in a relativistic expression for momentum as well, as we have already seen in another of our videos on relativistic momentum. P is equal to mu over square root of 1 minus u squared over c squared, and this can also be written as gamma times mu. Here similarly we can write of course energy, also total energy, as gamma times m c squared. Right, now these two expressions for energy and momentum respectively lead to an expression that connects both these quantities, that is the total energy E and the momentum P. That is, E squared is equal to mc squared whole squared plus P squared c squared. For massless particles such as photons, for example, this turns out to be E is equal to Pc. Because in the place of this m, we got to substitute m is equal to 0 for such particles. Let's move on to another expression for the total energy, which is the sum of rest energy and kinetic energy. So total energy gamma mc squared is equal to kinetic energy plus mc squared, from which we can get an expression for the kinetic energy Ke is equal to gamma times mc squared minus mc squared. That is, kinetic energy is a difference between the total energy and the rest energy, that is mc squared. Right. Let us move on to solve the problems now. Some of the problems. The first one, a proton moves at a speed of 0.95 times the speed of light c. Calculate its rest energy, total energy, and kinetic energy. So it's a straightforward problem. The first part is, let's say we calculate the rest energy A. Rest energy. That is, we know for the proton, we can write an expression specifically indicating proton mass as m suffix p c squared. So this is nothing but mc squared equation. So the mass of the proton can be taken to be 1.66 into, up to 2 decimals only I'm taking, 10 power minus 27 kg. So if we do it in kg, it is going to be the energy unit is going to be joules or kilogram meter squared per second square. So the velocity of light c is taken to be 3 into 10 power 8 meters per second. So when I square it, I get 9 into 10 power 16. So if I work this out, I'm getting 1.49 into 10 power minus 10 kg meter squared per second squared, which is nothing but joules. This quantity is joules. So we have this can be converted again actually back to MeV units, which is very convenient in special relativity for many energy calculation problems. Over 1.49 into 10 power minus 10 over the charge of the electron 1.6 into 10 power minus 90, and that converts that joule units to EV. So we get the answer in EV. So in EV units, if I work it out, I'm getting 0.93375 into 10 power 3 EV, and conventionally energy values can be expressed in million electron volts, so MeV or mega electron volts. So we can write the same thing as 933.75 MeV. This is the rest mass energy of an electron, or rest energy rather of protons, right? Protons. The next part is calculation of total energy, which is nothing but gamma mc squared. Therefore, E is equal to gamma mc squared, and then here it is 0.95 C, because total energy depends on the speed at which the particle is traveling. So we say U is equal to 0.95 C as given in the question. So first let's calculate gamma separately. That is 1 over square root of 1 minus U squared over C squared. That is 1 over square root of 1 minus 0.95 whole square. That turns out to be 3.203. Now we can plug in directly here, right? So for the proton, the total energy turns out to be, now gamma times this 3.203 times the rest energy, which we already calculated to be as mpc squared, 933 points. So now the total energy E is equal to gamma mc squared. We have calculated gamma to be 3.203. So 3.203 times the rest mass energy, which is mpc squared. So that is 933.75 MeV. And therefore the total energy in this case is 2991 MeV. This is the total energy of the proton, right? Now we can calculate the third part, that is the kinetic energy. Ke is equal to, it's just difference between total energy, that is gamma mpc c squared minus simply the rest mass energy mpc squared, and therefore Ke is the difference between this value 2991 MeV minus this 933.75 MeV. Since the units for both in MeV, we can directly write Ke to be equal to 2057.25 MeV. So this is the kinetic energy of the proton traveling at a velocity u is equal to 0.95 times the speed of light c. Now this can also be of course written as K is equal to 2.057 giga electron volts in terms of GeV. Either way it's okay, right? Let's move on to the next one. The kinetic energy of an electron is 5 times its rest energy. What is its total energy and what is its speed? Kinetic energy Ke is 5 times its rest energy, which is here in this case it is electron, so we can very well suffix it with an E. So the rest mass energy or the rest energy of the electron is MeC squared, which is we can calculate This value directly also we can write as 0.511 MeV. That is by taking electron mass alone to be equal to 9.11 into 10 power minus 31 kg. C squared is going to be 9 times 10 power 16 m squared as minus 2 squared minus 2. And if you multiply it and then convert that in its these two quantities, if you multiply and then convert from joule units to MeV units, we'll end up getting this number. Right. Now here kinetic energy expression, we are familiar with it. That is gamma mc squared minus mc squared. That is 5 times the rest mass energy. So we can write this as also gamma minus 1 times mec squared. I'm just suffixing here because it is mass of electron. So I'm suffixing E here. Now this is K. Right? So the kinetic energy is given by this expression, and this is equal to 5 times the rest mass energy, which is mec squared. Therefore, straight away we can say that these two quantities tally out, and therefore we have gamma to be equal to 6. Because gamma minus 1 is equal to 5. What is the speed? The speed is equal to, let's call it u, that can be obtained from the gamma equation 1 over square root of 1 minus u squared over c squared is equal to 6. So square root of 1 minus u squared over c squared is 1 by 6. So 1 minus u squared over c squared is 1 by 36. So u over c is 1 minus 1 over 36 square root. Right? So that is going to be point 9860. That is the speed with which the electron has got to be traveling for its kinetic energy to be 5 times its rest energy. So we can just write directly u now. Therefore, the speed of the electron u is going to be just 0.9860 c. That's it. Let's move on to the next one. What is the speed of a particle whose total energy is 50% greater than its rest energy? The total energy expression is E is equal to gamma mc squared, and the total energy here is 50% greater than rest energy. Rest energy is just mc squared. So therefore we can write an equation where this gamma mc squared is equal to 50%. So I'd say 1.5 times the rest energy. And this tells me directly that my gamma is 1.5, and therefore I can directly write that is equal to 1.5. And therefore 1 over 1.5 is my square root of 1 minus u squared over c squared. And you get work this out, I get speed u is equal to 0.7454 c. So that is the speed of a particle whose total energy is 50% greater than its rest energy. Right, let's go to the next one. That's the fourth problem. A high energy accelerator accelerates proton to a speed u with a kinetic energy of 50 giga electron volt. Determine its momentum and speed. So we have two parts. First we make the momentum and then the speed. So first we have high energy accelerator is accelerating the particle. So we have an, let's say, energy expression gamma mc squared for the total energy, and that is partly kinetic, and then the remaining is the rest mass energy. In this case, for the proton, we know that the rest mass energy, let's call that mpc squared, that is 933.75 in MeV units, right? So we can write this in GeV as 0.933 or maybe 934 directly, or I'm rounding it off here, GeV. And then here we can substitute this number, and then K is 50 is given. So the total energy in this case E is equal to gamma mc squared, and that is 50 GeV plus 0.934 GeV. So the total energy is 50.934 giga-electron volt. This is the total energy of the proton that is accelerated, and this is 50.934. Okay. Now for this proton, we have to calculate the gamma. So gamma mc squared is 50.934 eV. mc squared is 0.934 eV. So gamma times 0.934 GeV is equal to 50.934 GeV. Therefore, gamma is a ratio between these two numbers. So it is 50.934 over 0.934. We work it out, we get 54.53. This is our gamma. So that gamma, if you work out the speed, that is 1 over square root of 1 minus u squared over c squared is our gamma, which is 54.53. Therefore, u is equal to 0.9998 after the fourth decimal. We have that as the speed, times the speed of light c. Now from here on, we have to move to calculate the momentum first, right? First part is momentum. So the momentum of that particular particle is proton. In this case is P is equal to gamma times mu. Therefore, P is equal to gamma is 54, that is 54.53 times the mass of the particle, this proton here. So we can directly use either MeV units, or we can calculate in joules, and then in MeV, I mean kg s minus 1 units, and then convert into MeV over c. So that is also possible. Either way, it is fine. So I'm going to do the brute force approach here. That is 1.66 into 10 power minus 27 as the mass times the speed 0.9998 times the c, that is 3 to 10 power 8, which we have calculated in the previous step. So if I work this out, I am getting 271.51 times 10 power minus 19 kg meters per second momentum units. Now I have to convert, let us say, momentum to gamma mu momentum to MeV over c units. For that, I have to do 271.51 times 10 power minus 19, right? Over, since I want in MeV over c, I do 10 power 6 eV in the denominator, and I multiply by 3 into 10 power 8 again on the numerator, and then I have to divide by gain charge of the electron for conversion, right? So if I do this conversion and simplify this out, I am getting the momentum of the electron to be P is equal to 50.91 GeV over C. Instead of MeV over C, we can again convert further back into GeV over C. If you want in MeV over C, we have P is equal to 50,908.8 MeV over C. Either way, it is fine, right? These are the preferred energy units in special relativity for kinetic energy or total energy of the particles. Right. From this, of course, one can easily work out the speed. Speed we have already worked out here, so that is 0.9998 c. So that has been we have worked out before momentum. So that is essentially what is asked in the question. So what is the speed of a proton whose momentum and kinetic energy are the same as those of an electron traveling at the 0.75 times c? So here we have to compare the speed with an electron's speed, the values of momentum and kinetic energy. So let's start with let's just write down the speed that is provided to us, that is u is equal to 0.75 c. This is the speed of an electron. So we can calculate gamma as 1 over square root of 1 minus u squared over c squared, and that turns out to be 1.512. In special relativity, several problems. The first stage is to blindly calculate the gamma factor so that we can use that directly in the four equations. Here, kinetic energy of the electron. First stage is calculation of that, right? That is Ke or K, whatever we want to use for the electron, suffix E, okay, is gamma times the mass of the electron c squared minus the rest mass energy of the electron c squared, and that is 0.512 times 0.511 MeV, because the rest mass energy is this. I'm multiplying that by doing this gamma minus 1 directly here, because this expression can be further written as gamma minus 1 times MeC squared. Gamma minus 1 is 0.512, because it is 1.512 minus 1. And then multiply that with the rest mass energy of the electron, which is MeC squared here, which is 0.511 MeV. I'm getting 0.262 MeV as the kinetic energy of this particular electron. Now for proton, it has the same kinetic energy, but what is its speed? That is the question, right? So for proton, we have gamma and PC squared, let us say, minus rest mass energy of the proton is PC squared, so is this 0.262 MeV. Therefore, here also gamma minus 1 times MPC squared is 0.262 MeV. For proton, MPC squared is 933.75 MeV. So gamma minus 1 I directly write as 0.262 MeV over its rest mass, that is 933.75 MeV. That gives us a gamma very small one, that is 2.80 times 10 power minus 4. This is the gamma for the proton in this case. So sorry, this is gamma minus 1, right? So on the left side we have gamma minus 1. So we turn out to work out the gamma, that is going to be 1 plus this value. So for the fourth decimal accuracy, that is going to be 1.0003. Where 2 8 is round up estimate. Now for this gamma, you can calculate the speed, right? So the speed of the proton is gamma is this value, That is 1 over square root of 1 minus u squared over c squared is 1.0003. Therefore, u, if you work it out, you get 2.4 times 10 power minus 2 times the velocity of light c. This is the speed of the proton whose kinetic energy is the same as the kinetic energy of an electron traveling at 0.75 c. So because of the increased mass of the proton, you can see that its speed is slowing down. Right, momentum also is asked in this question. So we know that in special relativity we have a momentum expression P is equal to 1 over c square root of e squared minus mc squared whole square. This equation we have discussed in that at the beginning of this video. An equation or expression that connects the total energy and momentum of a relativistic particle. So here we can just plug in those values that we already got. 1 over c square root of total energy is 0.773 whole square minus the rest mass energy of the electron in this case, right? It is 0.511 whole square. Because electron total energy, once you know gamma, it's easy to find out, right? Gamma m v c squared is total energy of the electron. We calculated another gamma for electron, that is 1.512. 1.512 times 0.511 MeV. And that would turn out to be 0.773 MeV. This value we are substituting here. So we calculate the momentum based on that. So P is equal to, we are getting, if you simplify this whole thing, you get in MeV over C units as 0.58 MeV over C. Because already with the units have been taken here conveniently in MeV inside square root MeC square will get, right? So that out of the square root becomes MeV, already C is readily available outside. So this is the momentum of the electron. Now the proton has the same momentum, so we have to equate that to the proton momentum to calculate its speed again, right? It is the two different cases, right? So first we calculated from the energy the speed. Now we have to calculate the speed from the momentum, and again the same process has to be repeated. So we have to first equate this momentum to be the momentum of the proton. Let's call it P sub p. And we have the same expression here, which can be rewritten as the same expression for momentum and energy can be rewritten as P squared C squared is equal to gamma mc squared minus mc squared, where it's mp, it is mp, it is for the mass of the proton. So we can now write the gamma m p c squared as equal to p squared c squared plus mp c squared. We know that these values are, momentum is known to us here. We can substitute that value, square this value, multiply by c squared, we get directly 0.3364. Plus the rest mass energy of the proton is 933.75. That is the second term here. This would give us the total energy of the proton. That would be when we worked out gamma mpc squared, that is the total energy of the proton. That is 934.09. And from there again you can calculate the gamma for the proton by taking the ratio of this 934.09 over the rest mass energy of the proton. That turns out to be 1.0004 now for the proton. Now once we know this, we can use this expression gamma is equal to square root of 1 over square root of 1 minus u squared over c squared expression and calculate the speed of the proton. In this case, that turns out to be 0.004 027C. So the steps are repetitive. So I'm not working them all out here, right? Right, let's move to the next one. That is, so calculate the speed and kinetic energy of protons accelerated to an energy 400 times their rest energy in an accelerator. So in a particular accelerator, protons are accelerated to 400 times their rest energy. So we have to calculate the speed and kinetic energy. The first part we have to calculate the speed. That is part A. Let's call that. So E is equal to 400 times the rest mass energy, right? That is 400 times mp c squared for the proton, and that is equal to 400 times this value 933.75 MeV for the proton rest mass energy. So the total energy in this case is therefore 373.5 in terms of giga electron volt GeV units. This is such a high energy, so we have to preferably write it in GeV over the GeV units, right, for energy. So gamma mpc squared therefore is 373.5 giga electron volts. From there we can calculate gamma, which is a 373.5 GeV over the rest mass of the proton in GeV units is minus 0.93375, so we write as 8. So the gamma turns out to be, in this case, 399.98. 399.98 is the value. From there, we can calculate the velocity using our velocity of the proton using the expression 1 over square root of 1 minus u squared over c squared for gamma, and then we get the velocity as 0.9999c. From here, we can calculate the kinetic energy. Kinetic energy is total energy minus the rest mass energy. The total energy we have calculated to be 373.5 GeV. Rest mass energy is 0.9338 GeV, and therefore the kinetic energy is 372.57 GeV. This is the kinetic energy of this proton. So we have both calculated the speed as well as the kinetic energy, which are our two parts in this problem. Let's move on to the next one. Calculate the mass released as radiation by sun. If it radiates about 4 into 10 power 26 joules of energy into space each second, if the solar mass is 2 times 10 power 30 kg, how long will it take for sun to exhaust all its mass as radiation at the present rate? Right. So the solar mass, let me call that as m. So it's sun. That is given as this. So at the present rate, how long it will radiate, right? Now here we have another value here, that is the radiation released by sun per second, that is 4 times 10 power 26 joules. Now what is the mass equivalent of this value? First let us calculate that. So mass equivalent of the radiation, that is 4 times 10 power 26 joules. That can be easily obtained by dividing this by c squared. So then we have an expression mc squared is equal to the energy. The mass energy equivalence is brought in here. So we have 4 into 10 power 26 over 9 into 10 power 16, and that would be 4.44 into 10 power 9 kilograms. This is like 4.44 billion kilograms. That is a mass that sun loses every second as radiation. Now from there, how long will it take for sun to exhaust? That becomes our second part, right? So how long will it take for sun to exhaust all its mass? That is 2 into 10 power 30 is its mass. Let's say that is divided by this rate which it is losing mass every second. That would give us about 0.45 into 10 power 21 seconds. That is given as about 1.43 into 10 power 13 years. Right. So that is the duration for which the sample go on according to the present rate of its radiation emission. But there are other factors that have to be taken into consideration to calculate the actual value, which is of course less than this value based on other estimates. Right, next one. The electrons in the cathode ray tube of a television set are accelerated by a potential of 50,000 volts. What are the speeds of the electrons in such a device? Using classical kinetic energy expression, that's the first part, and then again using relativistic kinetic energy expression, the second part. And how significant is the difference in these speeds? Classically, we calculate the kinetic energy for that electron, how much it varies from the relativistic expression if we calculate using the relativistic expression for kinetic energy. That is the question here. So in both cases, we have to see the speeds, right? So first, let me calculate the speed of this particular electron in a television set accelerated by 50,000 volts potential, right? So speed, let me say that it is relativistic speed. Right, relativistic. We know the expression for kinetic energy relativistically, that is gamma minus 1 times the rest mass energy of the electron is the kinetic energy K. Here it is given as K is given as 50,000 volts because that can be directly written as 50,000 volts can be written as directly 50,000 EV. That is the kinetic energy. That is K 50 keV, right? 50 keV. So here the left side we have gamma minus 1. Again we have to write the rest energy of the electron, which is 0.511 MeV keV. That can be written as 511 keV. Because here we have 50 keV. Kilo electron volts. So gamma minus 1 turns out to be a ratio of these two. So 50 over 0.511. And that would be 0.098. So gamma becomes 1 plus this value. So it is 1.098. So for this gamma, we can easily calculate the speed using this 1 over square root of 1 minus u squared over c squared is 1.098. Therefore, u turns out to be 0.413 c. So this is the speed of that electron if we use a relativistic expression. Okay, so for the same particle, we can calculate using classical expression as the second part. So speed now using a classical expression for kinetic energy, which is just half mu squared, right? speed. So half mu squared is a speed. U is a speed, so half mu squared is the kinetic energy, which is 50 keV. So mu squared is 100 keV. U squared is 100 keV. I convert into joule units because I have mass of the electron. Can use the directly the mass. So it is 10 or 10 power 100 times 10 power 3 EV. So again, I convert that into joules by multiplying that by 1.6 into 10 power minus 19. So that is over the mass. Mass here is for the electron, that is 9.11 into 10 power minus 31. So work here, we get the speed here u as 0.443 c. So now these two values are comparable because for relativistic speed, we got u, let's call that as relativistic, that is 0.413 c. Here let me call this as u classical. U classical is 0.443 c. Now these speeds are not very different in certain sense, but you are multiplying by speed of light, so this is a significant change in speeds. So how different it is, you can calculate the difference. That is about 0.03 c. So u difference is the speed difference between the classical and the relativistic values, and that is 0.03 c, and that is a significant speed. So in such cases, we have to see that the relativistic expression for the speed is more suitable because the speed is nearly half the speed of light. So using our relativistic expression is more accurate in such scenarios. That is the conclusion we can arrive at. Right, in a particle collider, 9 giga-electron volt electrons are made to collide with positrons of energy 3.1 giga-electron volt, resulting in production of beam mesons and anti-beam mesons. Considering the energy difference between the electrons and positrons in this case, what would be the difference in their respective velocities? So here in a particle accelerator, rather collider, energetic electrons are made to collide with energetic positrons. Particle and antiparticle collision occurs, producing beam mesons and anti-beam mesons. Now, these are the energies that are given to a kinetic. Using these values, we can calculate the difference in their respective velocities originally. What is the velocity for the electrons as well as the positrons? So that is the question. So let's start from the expression for kinetic energy. The kinetic energy is gamma m e c squared minus m e c squared. M suffix e is the mass for the electron. That is given as 9 into 10 power 9 eV, GeV, right? So it is, let me write this as 9 into 10 power 9 eV is equal to gamma minus 1 times mec squared. Here in GeV units, we can write this as this is for the electrons, right? Or we can write in EV units also, right? That is also fine. Because here it is 0.511 MeV. Here left side is EV, so we can write multiply by 10 power 6 here also. So 9 into 10 power 9 EV over 0.511 into 10 power 6 EV gives me gamma minus 1, which I written on the right side. If I work this out and get gamma, I get 17,614 as a gamma value. For that gamma value, if I do the speed of the electrons, that is 0.9999, and then I have to continue for other 3 decimals, and then I get a number that is the 8th decimal place times C. This is for the kinetic energy of the electrons. If I do the same thing for the protons, Ke, that is gamma m, not protons here, sorry, it is positrons. Right. For positrons also, the mass is same as the electrons. Only we can write it as me plus c squared minus me plus c squared to indicate positrons, and then do the whole thing. The difference here is the energy is different, that is 3.1 GeV. So we can say 3.1 into 10 power 9 on the left side over 0.511 into 10 power 6 in eV. That would be my gamma minus 1. So if I work the gamma out there, I'm getting, because of the less energy, I'm getting only 6068 as gamma compared to the 17614 there. And then if I work out the velocity there also, I'm getting again 0.9999, and then I'm getting at around the 8 decimal some other value, maybe 6 or 7. So you can clearly see that in this case, the speed is varying only in the 8th decimal place, 7th or 8th decimal places. Because these two particles are accelerated to different energies, but their masses are same. The energies are accelerated to, the electrons are accelerated at thrice the energy, nearly thrice the energy of the positrons. The velocities are different only in the 8th decimal places. That is what we can understand based on this exercise. Right. Now, next problem. Calculate the momentum, kinetic energy, and total energy of an electron traveling at 3 different speeds, namely 0.020 C, 0.2 C, and then 0.9 C. Okay. So 3 different speeds are provided, and we have to calculate the momentum, kinetic energy, and total energy, all the 3. So momentum P, kinetic energy, let's call that K, and then total energy, let's call that capital E, of an electron whose speed is, we have 3 speeds, A, B, and C. 0.02 C, 0.2 C, and then 0.90 C. So in the first case, let's say A, that is speed is 0.020 C. For this case, if I calculate gamma, I'm getting 1.0002. For that gamma, if I do the momentum E, of course I can do in MeV over C units, or I can directly do the brute force. If I do directly MeV over C squared units, it's easy for me for the momentum. So gamma is 1.0002 multiplied by mu. I'll take the mass to be for the electron 0.511 rest mass in MeV units over C squared, because the rest mass is, it should be over C squared, and then multiply this with 0.020 C, so that I can cancel the C out and directly write momentum in MeV over C units, and that turns out to be 1.026 into 10 power minus 2 MeV over C. This is always easier if you work out in these units rather than doing it in kg meters per second units, because then again you will have to convert into MeV over C units for the numbers to look reasonably prettier than kg and over s minus 1 units, right? This is the, of course you can express this in keV to look more prettier. That is 10.26 keV over C. That is also uh, cleaner unit in this case, right? Right. Now, based on this momentum, of course, we can again use the velocities that is given and calculate the kinetic energy. For this case, it is gamma m e c squared minus m e c squared. Gamma has been already calculated as 1.002. So that can be directly calculated as Ke is equal to gamma minus 1. It is 1.0002 minus 1 times the rest mass energy, MEC squared for the electron, 0.511 MeV. Therefore, the kinetic energy, if I work this out, I am getting as 0.002 times 0.511 MeV. That is going to be 102.2 eV. This is a very small kinetic energy. And then if I calculate total energy, which is gamma mc squared for this electron, gamma is 1.002, mc squared is 0.511 MeV. So I get in keV units 511.10 keV. That is the total energy for this particular electron traveling at 0.020 C. So I calculated the momentum, kinetic energy and total energy of an electron traveling at this particular speed, which turns out to be 10.26 keV over C for momentum and 102.2 eV for kinetic energy, 511.10 keV for the total energy. All the three values I have calculated as the first part of this problem. These are the values. We can see that the difference between the total energy and the kinetic energy here, in this case, will turn out to be the rest mass energy, which is 0.511 that we can verify. Right? Now, for the second and third parts also, we can do the same thing. Work this out and get the values. The procedure is same, so I'm not going to just be repetitive here. I'm going to just write down the values for the other parts. For the proton travel, the electron traveling at speed 0.20 c here. That's 10 times higher velocity compared to the previous one. The momentum value turns out to be 0.105 MeV over C. There it was 10.26 keV over C. Here it is 0.105 MeV over C. That means it is, again, we can then say that it is in keV also. We can do that as 105 keV over C for comparison. This is the momentum. The kinetic energy in this case is 11 keV, and then the total energy in this case is 0.522 MeV. Okay. So that is the values. That's the value that we are getting. Again, the third part where the speed goes to 0.90 c, there you can calculate the momentum. That would be 1.058 MeV over C for momentum of the electron. The kinetic energy in that case would be 0.6612 MeV, and the total energy is 1.172 MeV. So I have provided these values so that people can work out and verify whether it works out the same. The next one, a mass of 80 kg, a mass of 80 kg is given a force of 8 newtons to be moved on a frictional surface. So we have a frictionless surface on which a mass of a frictionless surface on which the mass is moved with a force. This is 80 kg here, and a force of 8 newtons is provided. No other external forces are present in this case. Its mass energy increases by 25% for this object. How far the mass would move to raise its mass energy by this much? the distance to which this mass would move. That is the question here, right? So we can work this out using the energy expression, energy mass equivalence expression, mc squared. If I calculate the energy for that mass, the rest energy, so to say, is 80 into 3 into 10 power 8 over 2. Sorry, squared, right? So if I do this, I get 7.2 into 10 power 18 joules into units and that. Now 25% increase in this value is what we are trying to work out. 25% increase. So 25% of that value is 1.8 into 10 power 18. So now increasing is finally the energy goes to adding these two, 9 into 10 power 18 joules. That is the value to which the total energy would go. So this becomes from total energy of the object. Alright. Now this is moved with a very small force, so we don't have to use any relativistic expressions here in this case further. Just the mass energy idea is to be worked out here. Other than that, the classical expression for kinetic energy would be sufficient to work out the velocity for this particular object. So that is half m u squared, let me call that, is the kinetic energy part. That is the increase in the rest energy, right? That is the increase in the mass energy by 25% is attributed as the kinetic energy in this case, right? That it has to be the kinetic energy. So that is half m u squared is 1.8 into 10 power 18 joules. So if I work that out, I get the u squared as 4.5 into 10 power 16 joules, and therefore the speed alone of that object is 2.12 into 10 power 8 meters per second. Yeah. So this is a significant speed. Right. Now we can do for the distance that this is moving, we can use two equations, simple classical equations. V is equal to u plus at. Since we have taken the velocity to be u here, here this u is the velocity of the object, here the u becomes uh, the initial energy. So let me convert that as V naught. This expression again, right? V is equal to V naught plus at. And similarly, we have another expression for the distance moved, that is S is equal to V naught t plus half at squared. So since here V naught is initially, the object is at rest, V naught is 0. So we have one expression here, that is time is V over A. And then here another expression again, this is also 0. So we have another expression for S as, if you substitute V over A here in this time also, we get S as V squared over 2A from these two equations. And therefore we can work out S directly with the acceleration. In this case is A is equal to force over mass. Here force is 8 newtons. So 8 newtons over 80 kgs, that is 0.1 meters per second squared. That is the acceleration in this case. Right, using these things, we can now work out this thing. If I work out S, for example, that is half of V squared over 2A, A, this 2 is here. And that would be 2.12 into 10 power 8 over 2 into acceleration is 0.1. If I do that, I get the 22.5 into 10 power 16 meters. That is the distance over which this object will move. So it has to move such a long distance before its mass energy uh, increases to 25% of 1.25 times its original mass energy. That's 25% increase in mass energy. That is what is given here. So this is the value you get. This is 10 power 16 meters. That's a large distance. Right. Right. Next problem. Calculate the speed of an electron when its kinetic energy is 10% its rest mass energy equal to rest mass energy 10 times its rest mass energy. The first case 10% its rest mass energy, kinetic energy. So I directly write KE is equal to 0.1, 10% is 0.1 times this rest mass energy mc square. That means in my expression gamma minus 1 m EC squared for the kinetic energy, I get 0.1 MEC squared. Comparison tells me that gamma minus 1 is 0.1, therefore gamma is 1.1. For this gamma, if I calculate the U, I get 0.4166C. So speed I have calculated for the first case. Right. Next case also same thing I can do, repeat this whole process, same process. Now K is equal to rest energy, right? So that is K is equal to mc squared. K here we know that is gamma mc squared minus mc squared. That is equal to mc squared. Therefore, gamma mc squared is 2 mc squared. Therefore, gamma turns out to be 2. So if I work out speed here also, I am getting nearly double this value, that is 0.866C. Right? Now 10% to equal to rest energy. Now it is 10 times its rest energy, the third part. That is again, if I work out, gamma mc squared minus mc squared is 10 mc squared. Therefore, gamma minus 1 is 10, gamma is 11 here. Now this, if I work out, 1 over square root of 1 minus u square over c squared is gamma, that is 11. Therefore, my u, which is the speed, is 0.9959C. You can verify these values in this case. Right. So that completes some of the problems that we wanted to do on the topic of relativistic energy. Thanks for watching.